Okay, homework number 6, problem Dr. C number 1 has a table and a block sitting on top of the table. Let's draw it by hand. M2, no friction between this block and the table, but on top of M2 there's another block, M1, and there is friction. I'm just showing you that there is friction. It'll be either kinetic or static depending upon which part of the problem we're working. So there's friction between M1 and M2, and you're pulling block M2 along with an ideal string which supplies a tension T. Okay, and now we're supposed to consider two situations. If T is small enough, M1 will basically stick to it, and we'll be worried about static friction between M1 and M2. Remember, no friction with the table. And you'll be able to pull along and accelerate both masses together unless you try to accelerate them too fast, above a critical acceleration with above a critical tension. Then M1 will start sliding with respect to M2, okay, and it'll eventually fall off the back, but we're not worried about that. Okay, so this is a standard Newton's laws problem, which means that we start with a free body diagram. It's pretty natural in this case to pick a horizontal coordinate system. Let's pick X in the positive direction, the way the tension is pulling, and Y up. And let's draw all the forces acting on each block. I'll start with M1. Okay, there's a force of gravity pulling it down. And there's a normal force from M2 acting on this mass. Okay, that's what keeps M1 from sinking into M2. And there's this force of friction between the two blocks, and it's going to try to pull M1, accelerate M1 to the right. So I'll just draw it here. It acts on this surface, remember. There's contact forces between things in contact. One of them is the normal force, one is the friction force. And this friction force will be trying to accelerate M1 to the right along with M2. And those are all the forces that act on M1. Now, M2 is a bit more complicated. Let's draw that. There's, of course, gravity acting down on it, M2G down. There's a normal force from the table acting up on M2. I can call it N table if we like, although I have it M2 in the written solutions. It doesn't actually matter. It turns out we won't need this because there's no friction between M2 and the table. But if there was friction, we would need it, and it belongs in the force diagram. We know there's a tension T pulling it to the right. And because M2 is in contact with M1, these forces, N1 and FF, are an action-reaction pair. So if M2 is pushing up on M1 with a force N1, then N1 is pushing down on M2 with an equal and opposite force, and the same goes for the friction. If M1 is being dragged along by a frictional force applied by M2, there's an action-reaction force slowing the acceleration of M2 by the amount of this friction. So those are all the forces acting on each block, and we're ready to get started with the question asked in Part A. Part A says, if both blocks move together, find the maximum acceleration and the maximum tension you can supply. And there's a maximum because remember that we're talking about static friction now between these two. They're moving together, and so static friction is less than or equal to some USN, the normal force between them. But to solve for the maximum force of static friction, the maximum acceleration, we'll just set these two things equal to each other, okay, realizing that that will only be true if you're at that critical acceleration and critical tension. So now we're ready to get started. Let's concentrate on M1 and look at the sums of the forces in the y direction on M1. What do we learn from that? Well, that's N1 pointing up in my positive direction, M1G pointing down, but the acceleration in the y direction is 0. So this tells us that this normal force equals M1G, and we'll need that because that will tell us what the friction is. How about the sums of the forces on M1 in the x direction? Well, there's only the one of them. That's the force of friction, and that has to be equal to M1A. Now, for the force of friction, we can substitute mu static N. Remember, it will be less than or equal to this, but we're using equal. And this is N1. So mu s N1, and for the normal force, we found up here that that's just equal to M1G. So we have mu s M1G, and that has to be equal to M1A. And so we immediately have that the A1, if you have the maximum possible force of static friction, equals, and these M1s cancel, so it's just equal to mu s g. So that's the acceleration. We could call that, if you like, the critical acceleration that you could have for M1. If you pull so that it tries to accelerate any faster than that, static friction can't do it, and it'll break loose and eventually slide off the back. But we also ask for the tension that you can supply to get this critical acceleration. And we can get this tension that you supply by considering the system to be both masses. Remember, they're stuck together now, so our system is both masses. The only external force in the x direction, there's a normal force in the table. In the y direction, we don't care. But the only force in the x direction, external, is the tension. So we can write the critical tension is equal to the total mass times the acceleration, the critical acceleration. The total mass is m1 plus m2 times a, critical, or just mu s m1 plus m2g. Okay, so that's our answer for the critical acceleration if both blocks move together. Okay, if you try to pull harder than this tension, the blocks will start to move with respect to each other. And that's what you're asked to analyze in part B. Okay, in part B, if you have a tension larger than this, okay, M1 will start to accelerate slower than M2 does and will eventually fall off the back, and you're asked to find the acceleration of each block. Now, actually, the only thing that changes in our acceleration in our equations for M1 is the use of kinetic friction instead of static friction. These are still the only forces in the y direction, and the acceleration is 0. This is still the only force in the x direction, but now instead of static friction, it's kinetic friction. So we can immediately write down, without reproducing all the work, that, oh, A1 in this case is just mu kinetic g. Okay, because all we're doing is changing the s to k's in this equation. And so that's done without too much work. How about for M2? Now for M2, we haven't actually analyzed that. We didn't write down an equation for it. We didn't need it to look at separately. We looked at M1 separately in the combined system to answer part A. But now we need to actually analyze the sums of the forces on M2 to make progress in the x direction. Okay, we don't care about the y direction, it turns out. Okay, so if we do that, we write down, okay, I've got tension pulling it to the right. I've got this force of friction acting on it to the left. That has to be equal to m2, the acceleration of a2. Okay, and so this then tells me that the tension that we're after is just, and I'll have to plug in for the force of friction. So the tension will be equal to m2a2 plus the force of friction, or I'll just write it this way for you. The force of friction is mu kinetic now instead of static, m1g. Remember, the force of friction we found up here, was going to be mu s m1g, but now the s becomes a k. Okay, so this is equal to m2a2, and I can solve this expression for the acceleration of 2. A2 will be equal to t minus mu k m1g divided by m2. And that's what I was asked for. If you have a tension larger than the critical, and so that would be a number you might be given, or presumably would be given, and you know the masses and coefficients of friction, this would be the acceleration of the second block. This would be the acceleration of the first block, and we know that this will be smaller than that. Okay, and so we're done.